Okay, last video for the manual, for now at least. We're looking at something called differential equations, which is basically looking at the derivative and trying to work our way backwards, just piecing it apart in x's and y's. We're going to be dealing with both functions of x and functions of y. Notice right here that we have the derivative dy dx equals some factor of x times some factor of y. In order to solve it, we basically have to get the function of y with the dy and function of x with the dx. And then eventually we're going to get y equals some function of x. Or at least something similar, because this doesn't have to be a y, it could be a t. This doesn't have to be an x, it would be a u, a w, a z, whatever we want. Let's go ahead and get started with some of these examples. They're going to go pretty quick here. I see that I have dy dx equals 2x over y. Please realize that if I have a over b equals c over d, whenever I have a proportion set up like this, if I want to move one thing, for example the d, over to the other side, it's going to change not only from left to right, but it's also going to go across this dividing bar. So it would wind up being d times a up here in the numerator. Similarly, if I wanted to move something from the left to the right, or from, I should say, like this a here, if I wanted to divide by a on both sides, now it's on the bottom on the right. So then d over b equals c over a. We're going to be working with that because that's going to happen a lot when we move something across this equation type relationship. Then we're going to be looking at how it changes to the other side. So for example, this y is going to move over to the top there, and this dx is going to move over to the top here. Then we'd have y dy equals 2x dx. Well, that's easy so far. What we're looking for then is, how can we figure this out? How can we solve this? Well, we know how to integrate 2x dx, and we also know how to integrate this. And just like any algebraic operation, when you do one thing to one side, if you do it to the other, then it has equal balance. It's the property of equality. So I'm going to integrate both sides. If I integrate the left side, that gives me y squared over 2. If I integrate the right side, that just gives me x squared. Now because these are indefinite integrals, I need a constant somewhere. I'm going to stick it over here on the right because I want to get that y by itself. I don't want to make my life harder for me by just adding more to the y. So now let's work our way through this. I need to multiply both sides by 2 to get rid of this 2 in the denominator. Then I'll have y squared equals. Now when I distribute this 2, anytime I change the constant by adding or multiplying or something like that, it doesn't really change it because it's just a constant. A constant times 2 is still a constant. So that's going to remain the same. But the 2 times the x squared, that does change. And then I look at this y squared here. Well, to get rid of that, we're going to square root both sides. We get y equals the square root of 2x squared plus c. So that brings us back to what we wanted. Y equals some function of x. And in this case, it's the radical 2x squared plus c. It's that easy, guys. Let's try another one. Very similar. Okay, here, again, I want to get this y to move with the dy, but the x to be away from that, the dx. Now, if I move the y across and the dx back over here, that would give me dy over y squared equals dx. Now, somebody might think, well, you don't have a function with the x. You always have a function. You have at least a constant 1 there. So when I integrate both sides, I do have something to work with. The integral of dx is just x. We're going to add our constant over here. And the integral over here, this is really y to the negative 2. And then if I use power rule, I'm going to add 1 to that power. So it's going to become y to the negative 1 over negative 1. Let's do some rewriting here. Y to the negative 1 over negative 1 is really negative 1 over y. And that's going to be equal to x plus c over 1. Now notice again that I have a proportion set up and I can multiply across, move things from denominator to numerator and so on. So I'm going to take this y and move it up here, and this x plus c and move it down there. That's going to give me negative 1 over x plus c equals y. Hey, I have y equals some function of x. I'm done. Let's move on. Alright, this one's got, it looks a little more complicated, but it's not. It's really not. We treat it just the same. We move this dx up with the x's. We move this y up with the dy. That gives us 3y squared equals x plus sine of x all times dx. And this over here has a dy. So we're going to take the integral of both sides. Let's do each one individually here. 3y squared, the antiderivative of that is just y cubed. If you don't trust me, it'd be the same as 3y cubed over 3, and the 3's are going to reduce. Equals, we have x, the first becomes x squared over 2. Sine of x, the antiderivative of that is negative cosine of x. And we're going to have our plus c. Now we have this y cubed, we want that to just be y equals, so we're going to take the cube root of both sides. So we're going to have x squared over 2 minus cosine of x plus c. We're going to take the cubed root of all of that. Or that all to the 1/3 power. Same thing. Next, let's keep on moving here. We have dy dx equals 4y. Now a lot of people want to move the 4 and the y, but all I really need to get rid of is that y. I'm going to leave the 4 alone. I just need to move the y. That would make it so that I have dy over y. If I take this y and move it over here, take the dx and multiply it up to the top there, equals 4 dx. Well, if I integrate both sides of this, now I'm getting to logs and exponential stuff. That's going to give me natural log of y equals 4x plus c. Well, in order to get rid of this natural log, I need to use each of these as a power with base e on both sides. So the e and the natural log, or inverse functions, they undo each other. That leaves me with y on the left. On the right, I have e to the 4x plus c. Now if you think about, if I have e to some power, a plus b, or for any base to any sum of powers, that was originally e to the a times, whoops, pardon me, take that back, e to the a times e to the b. Well, if I'm looking at e to the 4x plus c, that means it was e to the 4x times e to the c. Well, e to the c is just a constant. It's a number raised to a constant, which is still a constant. So this is really e to the 4x times c. So we're going to simplify that, and we're going to move the c out in front, just because we usually have a constant or coefficient out front. So it's c times e to the 4x. Done. Notice this difference though. Our constant is not being added, it's being multiplied because we had to deal with logs, and we used that constant in a power, which made it be multiplied out here. Let's try this one. Very similar, but leave that k, that constant, alone. We're going to have dy over y on the left if I move the y down. I'm going to move the dx to the top. I'm going to have k dx on top. On the left side, I'm going to integrate, and on the right side, I'm going to integrate. I get natural log of y on the left equals kx plus c. Now, if you remember the last one, this is almost identical. So the e and the natural log undo each other. Then we have c times e to the kx. This is actually a pretty common occurrence here. This happens a lot with exponential growth type of measurements. Alright, here we got something a little bit different, but still pretty similar. We have x times y here for our derivative, dy dx. Let's move the dx up with the x and the y down below here. That gives me dy over y equals x dx. When I integrate both sides, both these again are pretty straightforward. I get the natural log of y is equal to x squared over 2 plus c. Don't forget that plus c. Your constant of integration does matter. I'm going to raise both of these as a power with base e. On the left side, that kind of undoes itself, and we just have y. On the right side, because we have addition of power, this constant c is going to get pulled out front again. So it's c times e to the x squared over 2. Easy breezy lemon squeezy. Ooh, this is interesting. That's very different. Take a look at it. Why? State the obvious to yourself. Why is this different? Well, I have two variables, both in a power. And I want to somehow get 1 over here because I need my function dy dx or d whatever over d something else equals f of x and g of y. I got to get it somehow where it's two functions being multiplied by each other or divided, or somehow where they're two factors and I can move them across that equation. Well, I can rewrite this. E to the u and plus 2t is the same as e to the u times e to the 2t. Oh, that's going to be very helpful. So now I think I'm ready to start separating it. So I'm going to separate these variables. I'm going to move the 2t. Well, no, I'm not going to move the 2t. I'm going to move the dt up with the e to the 2t. Move the e to the u down here. So that gives me the integral of du over e to the u equals the integral of e to the 2t dt. Now for each of these, it would be a lot easier if I could somehow get it back to the original format where I have e to the function. Let's pick a different letter, like if I have e to the a dA, and I'm taking the antiderivative of that, that's just e to the a plus c, of course. Well, for these ones, I need to somehow make this substitution. First of all, think about this as u to the -1, so that's e times u that's negative. And this one, our little function that we need to substitute out, is the 2t. So over here, negative u is going to be equal to some other variable. We just need to pick a letter. Let's try w, just for fun. And that means -1 du is equal to dw. If I'm trying to get e to the w dw, I need that negative in there. So I need a -1 in here. Let's make some more space just to clue this out. If we rewrite it, this would have been e to the -u du. But I need a negative here. But if I'm going to multiply by a negative inside, I got to balance it outside as well. Similarly, over on the right, we have, let's pick a different letter. How about v equals, we're going to substitute out this 2t and say v equals 2t. Then dv equals 2 times dt. Okay, well then that means that we need a 2 here. It's not there. So I'm going to multiply by 2 on the inside, but I'm going to balance it by multiplying by half on the outside. Now I have my e to the v dv and e to the w dw. And I'm going to integrate each side and see what happens. Well, it's going to kind of wind up being e to the w equals e to the v plus c. Let's rewrite those in terms of w and in terms of u and t. That means e to the -u. Oh, this is a negative out here, by the way, because that's a negative, and we got a 1/2 on this part. So we should have a 1/2 here. Equals 1/2 e to the v was 2t plus c. I got some algebra to do here because I want to get this u by itself. That was my original numerator. That kind of tells me what to get by itself. So first I'm going to multiply both sides by a negative. If you didn't catch that, let me do it again. This time I'll do it in a different color. Let's say orange. So multiply by a negative, which makes the left positive and the right negative. Then I need to take the natural log of each side. And on the left side, that is going to undo my exponential function. I'll just have -u equals natural log of -1/2 e to the 2t plus c. Now I need to make this u negative or positive. Just like I changed before, I'm going to make that positive, and I'll make the left side negative. So there's my function. And it even has my constant of integration wrapped up in it.